Hello everyone and welcome to our 23rd lecture, Introduction to Derivatives, or Derivatives Part 1. In the previous lecture we learned about limits and continuity, so now we can use that knowledge to define one of the most important ideas in calculus and then forward in physics. They're called the derivatives, which is basically just a fancy name for rate of change in a point or a slope. But trust me, we will use these a lot, hopefully, so hang on to your hats and let's get started. First of all, why are they important and why are they a different lecture from limits? Well, limits describe what happens near a point, while derivatives are used to describe what happens at a point, or better said, how the function behaves at a point. It has a lot of uses, but those will be covered in the third lecture, as the first lecture is what they are. Second lecture is how to use them, or how to solve stuff using them, and the third one is where they are used. Okay, so today, the first part, we learn just what they are, and maybe to solve some examples using the basic formula. So, let's start with the ways to mark a derivative. There are a lot of them, so here is a meme with 4. This meme includes integrals too, so the top part is derivatives and the bottom is integrals. But it technically falls under the same umbrella here, as you will see when we get to integrals. We will be using the Leibniz notation and the Lagrange notation. So the Lagrange one has prime on top of the function, while Leibniz has d, or like delta. So delta of the function over delta of x. So the change of the function with the respect of change of the variable that the function is dependent on. So here, if we change x, the function value changes. The result of the function changes. So the change of the function dependent on the change of the variable, kind of like this. We will be using the Leibniz more as the lectures progress, because it's a lot more intuitive, I'd say. But yeah, for this lecture, I'll mostly be using Lagrange. But yeah, more on that later again. For now, I'll be using, as said, f prime of x. I think the prime should be in between here, but then again, what do I know? So, of course, if we will see something like r prime, so instead of y, there is an r in physics, we will know that we need to use the function of r. So whatever r would mean for that example, for instance, resistance in electricity, and we will need to derive that function to get something. But then again, we will learn more as we go, because this will be the template for the future lectures, even in physics. So let's meet with the formal formula, something that you will see now and probably never again. Why? Because you don't really use it when solving stuff. It's like multiplication. You learn certain products of numbers and then use that as a template. Also, some simple rules, but again, we'll get to that in a bit and the next lecture. So this formula states that the derivative of a function at a certain x value is a limit where h approaches 0 of f of x plus h minus f of x divided by h. So let's think, for example, if our function was just 2x, so f of x is 2x, then we would get something like this. We would, so remember back in functions, what I said, if you want to change the function, so transformations, remember them? So if we had a change of the function, so f of x plus 3, where would this x plus 3 happen? It would happen before we multiply with the 2. So same way here, we add the h to the x, and then multiply all of that with 2. We get this, and we get 2x plus 2h minus 2x divided by h. Now, we can cancel the 2x parts out, because, well, 2x minus 2x is 0, and then we cancel out the h's because we're left with 2h on top and h on the bottom. So we're left with just 2. If this was too fast, don't worry, I think I solved one step by step later. This is just an example for how this applies to different functions. But this formula basically tells us that the rate of change over a small interval, so the interval where h is nearly 0, so distance from the value you're looking at is nearly 0, basically that's how you define the rate of change. There's a very nice video I'm gonna play over the lecture here in a bit, so stick around for that. But wait, isn't rate of change just a different and fancier name for the coefficient, the one multiplied to x, determining whether the function is increasing or decreasing? And well, the one that determines how steep it is? Well, it is, exactly. And what is the formula for that? This is the formula for that. So this is the formula for slope or directional coefficient, whatever you want to name it. And we remember from a few lectures ago when I mentioned that we can replace the difference between two values with delta or d. So something like this. Yes, this is another way to write derivatives, like we saw in the meme, dy over dx. So this is where it brings us. But so if you write d over dx and then the function multiplied to that, mathematicians will probably just crucify you if you explain it like how I just did, but it's how physicists do it and it's easier to understand. So imagine that you divide the change of the function with the change of the variable. If the function is comprised of that variable, you have a derivative. So basically, when looking at small changes in values, we replace the y with dy and treat it like one variable. So if we had something like this, we would technically have two variables and you couldn't just factor out y and get 1 plus d. Because important, this is one of the most important rules you have to learn, that dy over dx does not equal to y over x. So if you remember anything from today, let it be this. Because now at chemistry level, for instance, we have certain physical chemistry stuff where we've... Okay, let's say my exam last time, the last one I had, we had certain measurements on mercury bubble or blob. And then we had to calculate the error that would be caused if the piston pushing out mercury to enlarge the blob. So basically, what would the acceptable error for that piston be if we had a simple margin of error for the size of the blob? And then you have to realize that the change of the volume is based on the change of the height in the piston, so like a cylinder, and then you have to divide that with the actual volume of the sphere and stuff like that. You'll see when we get to physics. Basically, just remember that dy is treated as a single variable. Or to be more... Actually, we work with that a lot, so just remember dy should not be cancelled or factored out. Treat them as separate variables. It will help you out a lot. So this is a visual representation of the derivatives. I will skip forward to me using the PhET simulation linked here, and a overlay of the video, which, well, is playing on right now on the screen. As you can see, there's a single point that we have selected, and then we select another point far away, and we connect them with a straight line. Then we bring these two points together, so one approaches the first one, and then that slope is adjusted accordingly. And once the points touch, that slope should be the slope or the value of the derivative at that point in that function. So the steeper the function, the higher the value. But we see that in the PhET animation, to which I will skip and then return back to the video. So this is slightly scuffed, so I do apologize for this, but I will draw the... Sorry, like this. On top, we have a function, as you can see here, f of x, and on the bottom, we have the derivative. So basically, the top part is representing a function. So let's say we make something like this, and bring this closer, and then bring this up, and then bring this up, and then... So something like this, okay? This is our function. And on the bottom, we have relative change of the slopes. So if we look here, the slope is 0, so this arrow, and as we move it up, the value here stays 0. But as soon as this arrow here slightly tilts, okay, this is a lot more responsive than the top part, but as this one tilts or changes, so does this. So for instance, in this point, the value of derivative here should be right around 1, because the point goes from here to here. And we can see that if this represents 1, it's here as 1. Then we make it halfway to the top, and then it starts turning down, while still being positive. So in the middle of the slope is where the derivative is the highest. as you're reaching the top of the slope on the function, the derivative will slowly decrease towards 0. So anything above this x-axis in the bottom graph represents increasing. The higher it is, the faster it is increasing. The closer to the line it is, the slower it is increasing. In this case, we see that we're barely above 0. In this arrow, we see it's slightly more upwards than it would be flat. So at point 0 on this graph, this one is relatively flat. As soon as we get into the negative, it starts falling down. Once we get to the middle of the slope here, before another change, this peaks and starts turning around. The behavior like this is not important. It's important to know that once the derivative is above 0, which I'll repeat later, this one is increasing. And when it's 0, it's flat. When it's negative, it's decreasing. And so on and so on. So, of course, this shows us that we can graph derivatives, so derivatives of a function, and we can also graph second derivatives of a function, more on which later. But in chemistry, we will be using them for something very cool, so stay tuned and I'll pass you forward to the future next, recording the second part of the lecture. Thank you, past next, and let's continue. So we saw that to find a derivative of a function, we basically take a tangent to the graph at that point, and the directional coefficient of that line is the derivative. Now let's do it for something that we will learn to solve faster way next time. So for when the function given is x squared. We see that the coefficient slope is 1, so the answer is 1, right? Well, no, but let's solve to prove it. So we bring out our formula and we insert the values and then we square them because, well, the function is basically squaring the x. We change the x to be some h value higher than x, and then we square it. Basically, that's sum. We break apart the brackets. We cancel out the x squared because x squared minus x squared is 0. And then we cancel out, we can factor out h's and then cancel them out. But we can also just cancel them out because we're smart enough to do that. So cross 1 here, cross 1 here. So I cancel the square here because one h still remains because there's two h's here. And the bottom h disappears. We're left with this. And as we remember from last time, now that we don't have an indeterminate form, because here we had 0 plus 0 divided by 0, which is indeterminate. Here, this doesn't happen. We can insert h as 0 to determine the limit. And that's 2x. This is our derivative. So the derivative of this function is 2x. It tells us that at a given point, a random point we choose on the function x squared, slope at it will be double of the x value at that point. So let's take this. These are some of the points from the graph. So at a point 4, 16. So we take 4 and square it, we get 16. Our slope is 8. At the point 5, 25, the slope is 10, and so on and so on. So we can see that the slope changes as the function progresses. We can also see that the y changes aren't really equal to the change of the derivative. That's because the coefficient predicts linear behavior, but our function isn't linear, so sadly we can't use the derivatives to predict a next point with huge precision, especially if it's so far away, because remember, h is approximated to be 0, while this is one whole unit. If it was like 0.00001 unit, maybe you would get close. You have to test it for yourself, but the further away it is, the less accurate it is. So, of course, there are ways to check if the slope is relatively the same in a certain area and then assume that it's linear there. That's very helpful for standards and calibration curves in chemistry, but that's still a few years away, so I won't bother you with that. Basically, you get the derivative by following this formula, and it's not always just the directional coefficient, and it can also be dependent on the x. Now, if you remember my PhET simulation, the one that I dragged on for some reason, and I said I'm gonna explain later, the bottom, the red one, drew a function of the derivative values. You can draw functions of other derivatives, as I said, and both of these have their uses that we will explore further in chemistry and physics. But it's nice that I mentioned them here because it's a baseline. And while on topic, here is a rule that just because we have a value of a function that is negative, it doesn't mean that the slope has to be negative too. So in other words, the sign of the value of the derivative is independent from whether the function has a positive or a negative y value, as increasing slope is positive derivative and decreasing slope is negative derivative regardless of their y values. We remember the function, as I said, when it was above the x-axis, the red one, it was increasing. And when it fell down, even though the value was still positive on the normal function, the derivative was negative. Again, this is summed up. If the derivative is less than 0, then the function is decreasing. If the derivative is more than 0, the function is increasing. And if the derivative is exactly 0, we either have a saddle, extremum, or just a constant. So what the hell is an extremum or a saddle? Well, this is it. Extremum is a common term for maximums and minimums, and those are divided into local and global ones. But more on that in the third part of the derivatives, because it's the uses of the derivatives. Basically, they are a point when the sign of the derivative value changes. So before the 0, it's positive, and after it's negative, and vice versa. As we can see, graph goes up. So the derivative is positive, then it falls, becomes negative at a maximum, and then it's negative all the way down to the minimum, and then it becomes positive as it goes back up, and then turns again at the maximum, and then we approach a saddle. A saddle is a point where the sign stays, so the function, the derivative of the function is negative, becomes 0, and then becomes negative again. Basically, this is it. This is the point. Well, this will give us a lot of uses just from this very property we see here. So it's important to remember how this behaves. So these are higher derivatives. Another way of noting higher derivatives is just a bracket of n. So the first derivative is 1 prime. As I said before, this is also, I think, more correct way to mark it, because you put the derivative on the function, not the variable. But then again, the variable is the one that changes. So the first derivative is marked something like this. So inside of a bracket, so it's not like an exponent, because just a 2 over the f would tell us f squared. So we would get any value inside of the function squared. So inside the brackets denotes higher derivatives. We won't be using them, don't worry. Maybe second derivative at maximum, maybe third in some distant future if we're deriving from completely basic values, but don't worry. But nth derivative is this one. It will be slightly important next time because it will help us with the table for derivative values. And what they mean is basically just taking a derivative of the derivative. So first derivative is the derivative of the function. Second derivative is the derivative of the function. And the third derivative is the derivative of the derivative of the derivative of the function. Dear God, I forgot how to pronounce the word derivative now, I think. Anyway, the nth derivative just means applying it n times. And here is the mini test. It's basically using the formula and some other stuff. Basically, just some logic, you know. It's not very complicated, don't worry. I made sure it's simple. I had to make a mini test to check your knowledge today because, well, while this was a very short video, a lot shorter lecture than usual, it is still an introduction. Plus, we have 3 lectures dedicated to one topic, so each can be slightly shorter, allowing us to cover more width and get you more knowledge, while just distributing it equally so it's not overwhelming in one lecture, because covering everything would be a lot, trust me. But we can start off strong. And to make sure that we do, if you have any questions at all, really any at all, please comment down below so I can help you remove any misunderstandings, because I think this and integrals and differential equations are very important for the physics lecture, like the future chapters that I'm gonna have. Because we will, while yes, learning formulas for physics is important, we will learn how to get these formulas. So if you're ever stuck, you can find your own formula, because remembering a formula is pointless if you don't understand it, because then you're just gonna see a bunch of numbers and values and you're not gonna know what they do. So I'm gonna try to explain how to get the formula so you'll be able to understand it. But yeah, thank you so much for tuning in. I hope everything went well, and I'll see you all on our next quest. Bye.